Okay, number 47 is using the same directions as 43 and 45, actually 43 through 48. Write the integral as a sum of integrals without absolute value. So what's going on here, guys? They're asking us to evaluate the integral of the absolute value of cosine of x from 0 to pi. And I'll bet a lot of you guys would look at this and say, wait a minute, I don't know how to graph this without my calculator. It's really not that hard. Let me show you what I'm going to do. I'm going to completely ignore the absolute value for the time being, and I'm going to draw this thing just with a dotted line. Cosine starts up here at 1, and of course then it goes down, and it goes up, and it goes down. There you go. And that, more or less, guys, is one complete cycle of a cosine wave. Now I should probably, sorry about that, there we go, do that, and let's label things. One full cycle of the cosine wave takes us to 2 pi. So that would probably tell you that this trough occurs right here at pi, and this first x-intercept is half of that, which is going to be pi over 2, and I think that's as much as I'm going to do right now. Now, obviously, I graphed more of this than I needed to, so you know what? Let me just simplify things. Let me get rid of everything up until we got to pi right here. Okay, and that's what we're looking at here, guys. This is the graph of cosine of x without the absolute value. So now, how do I graph it with the absolute value? Easy. Everywhere that this function was already positive, the absolute value has no impact. And that occurs right here in the first quadrant. All of these y values here were already positive, so the absolute value had no impact. Then, as this thing now extends below the x-axis, all of our next group of y values would have been negative. The absolute value simply flips them and turns them into positive values. So now, that funky little curve that I drew right there, guys, this is what we're looking at. This region and this region right here. Now, let's talk about what we're doing with this. This integral then can be split up. And my first region, I'll call this region number 1, starts at 0 and ends right there at pi over 2. And that is the function then cosine of x taken with respect to x. Now, really, if it were up to me, I would evaluate this problem simply by doing this. Sticking a 2 in front of that integral. Because I think everybody can see that region number 2 right here is symmetrical. It's identical to region number 1, so I could just find the area of region 1 and double it. That would be the smartest way to do this problem. The only problem is that doesn't actually satisfy what they wanted us to do right here. So what am I doing instead? I'm going to add to this now a second integral, starting at pi over 2 and ending when x is equal to pi. And now the question is, guys, what function is this right here? Well, it is the reflection of this cosine of x graph underneath it. Then what we're dealing with here, guys, is y equals the opposite of cosine of x. So that's going to go right here, the opposite of cosine of x taken with respect to x. And I guess at that point, this negative right here, I'm going to go ahead and pull that out in front of the integral. That's going to make my life a lot easier. So let me get rid of that minus, but then this plus right here becomes a minus. And now I feel pretty good about where we're at here, guys. So let's see what's going on. Antiderivative of cosine. What function has a derivative of cosine? That would be the sine of x, evaluated from 0 to pi over 2. And then minus, same deal now, antiderivative of cosine of x is sine of x. And we're going from pi over 2 to pi. All right, guys, let's see what we can do. I'm going to scroll up a little bit, and here we go. I'll start right here, putting a pi over 2 in for x here. And the sine of pi over 2 is going to be 1 minus, and then it'll be the sine of 0 going right here, which is 0. Minus, start another set of brackets now. Let's put the pi in here first. The sine of pi is going to be 0 minus the sine of pi over 2, which is going to be 1. So let's just be careful not to make a silly little sign error here. 1 minus negative 1, which of course is 1 plus 1, and our answer there is 2. which, if you remember a problem that we did in class, what we came up with a while ago is that the area, let me sketch this thing real quick, that the area of one hump of either a sine wave or a cosine wave, it doesn't really matter which one you do because they're identical, the area of one hump right there is equal to 2 square units. And that is equivalent to what we have right here, guys. It's just been split up and redistributed a little bit. So yeah, I was kind of expecting that answer of 2 right at the beginning of the problem. But that's how you do problem number 47, the proper way, with the directions following what they asked us to do there. So that's 47.